Hey there, everybody. This is Mr. Schnitzius. I'm one of the A Squared I geometry teachers. And in this video, we are going to work through the third embedded assessment at the end of Unit 1. You can use this to check your understanding for how well you understand how to use geometry and algebra together like you've been doing in the last couple of activities. Just like in all of the other embedded assessment videos, I'm really going to encourage you to pause this video, work all 6 of these problems out by yourself, and then come back and check your answers while we discuss them together. Okay, go ahead and take a second to do that. Okay, so let's look at all 6 of these answers. We've got a picture of a roller coaster here. And the problem setup says the first hill of the Steel Dragon 2000 roller coaster in Nagashima, Japan, drops riders from a height of 318 feet. A portion of this first hill has been transposed onto a coordinate plane and is shown to the right. Number 1 says the structure of the supports for the hill consists of steel beams that run parallel and perpendicular to each other. The endpoints of the beam shown by segment BC are 0, 150 and 120, 0, and the endpoints of the beam shown by segment AD are 0, 125 and 100, 0. Part A says verify and explain why the two beams are parallel. So the goal is to show that segment BC is parallel to segment AD. Well, we've got to think, how can we do that? What do we know about segments, also lines that are parallel? Well, we know that they have the same slope. So if we can calculate the slope for segment BC, and we can show that it comes out to be the same thing as the slope for segment AD, we'll be in business. So you should have seen in your previous activities that the slope formula is y2 minus y1 over divided by x2 minus x1. So this first problem is pretty simple. We're just going to work out those two slopes. The slope of segment BC is going to be, and I always like to label my coordinates. So I'm going to label this 0, 150 as x1 and y1. I'm going to label 120, 0 as x2, y2. So let's just plug those values in. That's going to be 0 minus 150 divided by the difference in the x values, 120 minus 0. So in the numerator, that's going to work out to be negative 150. In the denominator, that's going to work out to be 120. So let's go ahead and leave it like that just for now, and then we'll see what happens later on. All right, we're going to do the same thing for the slope of segment AD. And we're going to use the same slope formula. In order to very easily know where to put the values in, I'm going to very carefully label the coordinates, x1 and y1 for point A, x2 and y2 for point D. And of course, you learned this in Algebra 1, but it doesn't really matter which point gets labeled x1 and y1. It doesn't matter which point gets labeled x2 and y2. I could put x2, y2 here for point A. I could put x1, y1 here for point D. That wouldn't make any difference. I guarantee you it would come out to be the exact same. What you have to be sure of is that x1 and y1 go together. If I put x1 as 0 and y2 as 125, then you would actually have a problem. So let's look at what this gives us. We've got y2, 0, minus y1, 125, divided by x2, which is 100, minus x1, which is 0. So in the numerator, we get negative 125 over 100. Okay, so how does this help us? Because right now it's hard to see what the relationship between these two slopes is because they're unreduced fractions. So if we can simplify these fractions, if we think what's the greatest common factor of 150 and 120, that would be 30. So we can divide the top and bottom by 30 and get negative 5. 30 goes into 155 times. 30 goes into 124 times. So that's our reduced fraction for the slope of segment BC. And we could do the same thing for the slope of segment AD. If we want to reduce this fraction, we could say, what's the greatest common factor of 125 and 100? Well, that would be 25. 25 goes into 125 5 times. That's negative 25, so we want to make that negative. 25 goes into 104 times. And whammo blammo, we've got two slopes that are the same. So why does that help us? Well, we know that if two lines have the same slope, then they are parallel. So just showing that these two slopes are equal is enough to prove that segment BC and segment AD are parallel. We've done it. Okay, let's look at part B now. This says if angle DAB measures 125 degrees, and we know from the last problem that segments BC and AD are parallel, then what is the measure of angle CBA, this angle right here? Well, when you were learning about parallel lines that are cut by a transversal, you should have seen that there's a difference between interior angles and exterior angles. Let's first identify that this y-axis is the transversal. You know, that transversal is the segment or line that's joining the two lines. So this is our transversal right here. Okay, our angles DAB and angle CBA, are those interior or exterior angles? When I'm explaining this, I like to think about these two lines as like the ends or the sides of a grocery aisle. So let's say this is one freezer and this is another freezer. This angle would be in between those two freezers. It would be inside this aisle, right? Same thing for angle CBA. So these are two interior angles. I guess another question we could ask ourselves is, are these two angles same side angles or are they alternate angles? And that depends on their relationship to the transversal, right? This transversal connecting lines BC and AD, well, let's see, angle DAB is on the right side of that transversal, angle CBA is on the right side of that transversal. Since these two angles are both on the same side, the right side of the transversal, they're same side angles. So these are same side interior angles. And then we just need to ask ourselves, well, when two parallel lines are cut by a transversal, what's the relationship between the same side interior angles? Well, I'm going to add something to this answer. These are not just interior angles, they're same side interior angles. Okay, so you should have learned the same side interior angles theorem, either in one of the previous lesson videos or with your teacher. If two parallel lines are cut by a transversal, then the same side interior angles formed are supplementary. That's how we know that their sum is 180 degrees. Okay, so then it's very, very easy. These two angle measures have to add up to 180 degrees. We've already used 125 degrees for angle DAB. Therefore, we have 55 degrees left over for the measure of angle CBA. All right, let's keep on going. Number 2 says, determine the equations of the lines containing the beams from item 1 and explain how the equations of the lines can help you determine that the beams are parallel. Okay, well, this is also a review of Algebra 1. In y equals mx plus b form, we've got everything that we need as long as we remember that m is the slope and b is the y-intercept. All right, so we've already got both of the slopes. We saw in number 1, part A, that the slope for both of these lines is -5/4. That's why we were able to say we've proved that they're parallel to each other. So if I look at this first line, I know I'm going to do this one in purple. I know that the slope is -5/4. Okay, so I know that the equation is going to be y equals -5/4x plus something. All I need now is the y-intercept. Well, that's actually very, very simple because on a graph, you can recognize the y-intercept as the point where the line crosses the y-axis. This transversal is the y-axis. Even if I didn't have this graph, I know that the y-intercept is the y value when x is 0. Hey, this value of x is 0 right here. So this is going to be our value for b. So that first equation is going to be y equals -5/4x. Hey, there's the slope, plus 150, because 150 right here is the y-intercept. All right, same thing for line AD. We saw previously that the slope is going to be -5/4. We've got a smaller y-intercept because it's not as high up, but our y-intercept there is going to be 125. So pretty simple stuff. Same slope, same y-intercept. And then they want us to explain how the equations of the lines can help us determine that the beams are parallel. So we could say something like, since both equations have equal slopes, the beams must be parallel. So this is an example of how math could be important in your everyday life, right? If you're an engineer and you've been hired by this theme park to build this roller coaster, and you know that the designer wants these beams to be parallel, maybe you're a quality control inspector and you go out and you take some measurements. If you determine that these two beams have equations that don't have the same slope, then you're going to have to go back to your bosses or the builder or somebody and say, hey, this roller coaster might not be safe. We haven't built it correctly, so we need to go back and change something. All right, let's look at number 3. A third support beam is perpendicular to the beam shown by segment BC. If marked on the coordinate plane, the line containing this beam would pass through the points 60, 75. What is the equation of the line containing this third beam? Explain how you determined your answer. Well, what do we know about lines that are perpendicular? We know that the slopes are opposite reciprocals. Now, this should be a flashback to Algebra 1. You also learned about this week. Opposite reciprocals means we have different signs. That's what the opposite part means. Sometimes they're called negative reciprocals. That can be tricky, though, because if the slope is starting out negative and you say, oh, negative reciprocals, I guess it's still supposed to be negative. No, the negative really means that the two signs between the two slopes are supposed to be different. So I like opposite reciprocals a little bit better. So we already have our negative slope here. So our perpendicular slope is going to have to be positive. And reciprocal just means that you take the fraction and you flip it around. So what we know is that our perpendicular slope is going to be 4 over 5. But we also know that it has to pass through this point. So what is the equation of the line containing this beam? So they got a final answer, and we're going to step through the work of how you get this. Y equals 4 over 5x plus 27. So they got the same perpendicular slope right here. Now, if you have a slope and a point, 60, 75, you can use point slope form. Great algebra review, this activity. So point slope form is y minus y1 equals m times x minus x1. Well, we've got our slope right here. We've got coordinates from our point. So we can just take those coordinates and substitute. Y minus 75 equals 4 over 5 times x minus 60. And then we're going to distribute. We're just going to solve this, put it into slope-intercept form, keep moving things around until we have y by itself. So 4/5 of 60, if you want to do that in your head, 1/5 of 60 is 12. 12 times 4 is 48. We want to bring that negative sign down. All right, we've almost got everything. We just need to move that 75 over to the other side. So we're going to add 75 on both sides. What's the final equation going to look like? Well, those cancel out. So we've got y equals 4 over 5x plus 27. And this is most definitely a sketch, okay? If I was going to take a guess at what that's going to look like, I'd say 27 looks like it could be about there. And then we need the line to run perpendicular to segment BC. So I would say it would look something like that, so that we could say that we had a right angle right there. And you could also say by the one of the theorems that you learned in your activity, I think it's the perpendicular transversal theorem. If this transversal is perpendicular to one of two parallel lines, therefore it has to also be perpendicular to the other parallel line. Why is that? Well, these are corresponding angles, right? If parallel lines are cut by a transversal, then the corresponding angles formed are congruent. Alrighty, little bonus information there, free of charge. Okay, number 4, 5, and 6, shift gears a little bit. We've got a new picture. This is a section of the steel support structure. So we've got some given information here. Given that segment JK is parallel to segment PL, given that the measure of angle JKL is 10x plus 5 degrees and the measure of angle PLK is 12x minus 1 degrees, what is the measure in degrees of angle JKL and angle PLK? Well, let's see. Angle JKL, that's this angle right here. Angle PLK, that's this angle right here. So not just angle 2, but from JK all the way to side KL, from PL all the way to side LK. Okay, well, just like we did in number 1B, are these interior angles or exterior angles? Well, they're interior angles. They're in between these two parallel segments. Are they on the same side of the transversal or on different sides of the transversal? Well, if we think about KL as our transversal, they're both on the left side of segment KL. So it looks like those are going to be same side interior angles. Let's see. So same thing before. I'm going to add in here that these are not just interior angles, they're same side interior angles. The sum of their measures is 180 degrees. So that gives us this equation that I wanted to go through and actually solve out. We can combine the like terms. So 10x plus 12x is 22x. We can combine the constants. Positive 5 plus negative 1 is 4. So since parallel lines cut by a transversal gives us same side interior angles that are supplementary, the sum of these two angle measures has to be 180 degrees. So now we've got a pretty easy equation that we can solve. We can take 4 away from both sides. So now we've got 22x equals 176. The inverse of multiplication is division. So that's going to give us that x equals 8. And you might think, oh man, what an easy question, I can move on. Not so fast. They're asking us for the measure of angle JKL and the measure of angle PLK. And it'll actually be kind of nice that they're asking us for those in degrees, because then we can use that to check our work, right? It's going to be, for the measure of angle JKL, 10 times whatever x is plus 5 degrees. Well, we know that x is 8 now, or at least that's what this equation told us. So 10 times 8 is 80, plus 5 more, that's going to give us 85 degrees. And the way that we can check that x equals 8 is really right is we better get an angle measure for angle PLK that we can add to 85 degrees and get 180 degrees total. If not, something is goofed up. Well, let's see. This is 12 times something minus 1 degrees. That's something. That x is 8. So 12 times 8 is 96. 96 minus 1 is 95 degrees. That is great news because 85 degrees plus 95 degrees is 180 degrees. We did it. All right. So let's look at number 5. Explain how an engineer could determine whether segment PN is parallel to segment LM by measuring two angles in the diagram. So their suggestion is angle NPM, and angle LMP, this angle over here. So now let's look at these two angles, because we're trying to see if this segment is parallel to this segment. Pardon my not totally straight lines there. Well, we've got a transversal connecting those two lines. That's segment PM. Third time's the charm. There we go. So now we could ask ourselves, are these two angles, angle NPM and angle LMP, are they interior or exterior angles? They're inside these two blue lines, right? We've got a lot of interior angles in this embedded assessment. This is our first time, though, that we've had two angles that are on different sides of the transversal. Here's our red transversal PM. Angle NPM is on the left of that transversal. Angle LMP is on the right of that transversal. So those are actually alternate interior angles. So if the engineer measures those two angles and finds out that they're actually congruent, if he gets the measure of angle NPM is the same as the measure of angle LMP, well then he can conclude that these two segments are parallel because of the converse of the alternate interior angles theorem. This is a good question to think about everything that you've learned so far, because this brings in what we learned about conditional statements in activity 3. Remember, the converse is when you switch the hypothesis and the conclusion. So instead of using the alternate interior angles theorem, if parallel lines are cut by a transversal, then the alternate interior angles formed are congruent. This starts at the end and works backwards. If we know that these two angles are congruent, if two lines are cut by a transversal so that the alternate interior angles are congruent, then the conclusion is that we can know that the two lines are parallel to each other. Two lines are, in this case, two segments. All right, last one. Number 6, write a 2-column proof. So we've got given information here. We're going to go ahead and mark that given information as we put it into the proof. The given information is that segment JK is parallel to segment PL, and also that angle 1 is congruent to angle 2. So we know that we're going to try to get this information to prove that angle 3 is congruent to angle 4. Well, we always want to put in our given information and then mark it in the picture. So segment JK is parallel to segment PL. If that is true, then we know that angle 1 is congruent to angle 3. How do we know that? Well, we know that because these are alternate interior angles. Here are two parallel segments. Here is our transversal, segment JL. Angle 1 and angle 3 are both inside these two lines. They're on alternate sides of the transversal, though. Angle 1 is on the right, angle 3 is on the left. So the alternate interior angles theorem says the lines are parallel and cut by a transversal, then the alternate interior angles formed are congruent. So that's pretty much all we can know based on this first piece of given information. So we're going to bring in our other piece of given information. That is that angle 1 is congruent to angle 2. Now, as soon as we have this picture set up like this, it's pretty obvious that all three of these angles are congruent to each other, right? If angle 1 is congruent to angle 3, and angle 1 is also congruent to angle 2, well, the only way this is going to work where all three of these angles are congruent to each other is if angle 2 and angle 3 are congruent. And we know that that's true because of the transitive property. Angle 1 is congruent to both angle 2 and angle 3. Therefore, angle 2 and angle 3 must be congruent to each other. So if you look at where we're trying to go, we're trying to prove that angle 3 and angle 4 are congruent to each other, right? We haven't said anything about angle 4 yet. But what's nice about this is we have another transversal that's connecting segments JK and PL. That's transversal PK. And look at what happens when we draw that transversal in. We've got another pair of alternate interior angles. Which angle forms an alternate interior angle pair with angle 2? Well, it's angle 4. How do we know that those two angles are congruent? Well, because they're alternate interior angles, just like angles 1 and 3 are. So that's the exact same justification as step 2. Now we can put it all together. Okay, if angle 3 is congruent to angle 2, if angle 4 is congruent to angle 2, well, by the transitive property, that means that angle 3 and angle 4 have to be congruent to each other. So now we've shown what we were trying to prove. Start with the given information, work down till you've used deductive reasoning to explain why this statement has to be true. And then once you get there, you're done. Start at the beginning, and then when you get to the end, stop. All right, so since that's the end of this embedded assessment, I'm going to take my own advice and stop here. Thank you guys so much for your hard work, and have a great day.